So we ended the last video with them thanking dark matter for our ability to exist in the universe. So let's talk about that idea a little bit. Let's map out the large-scale structure of the universe. So we'll put the sun here at the center, and we notice that the galaxies are not evenly distributed. You get clusters of galaxies, filaments connecting the clusters of galaxies, and also great big regions where there's very little. We call them voids. And it turns out that the spacing and the pattern of these filaments is very dependent on the amount of matter and dark matter and energy in the universe. So what we do is we do a large number of different simulations testing out what the universes look like with a little bit more matter or with a little bit less energy. And this is what our universe seems to have done. It used to be fairly smooth, but as time goes on, it clumps up into galaxies and then galaxy clusters. But you can't get this amount of clumping if you don't have any dark matter in your simulation. When the universe was just a second old, we would expect the dark matter, the red dots here, and the regular matter, the yellow dots, to be evenly spread out. They haven't had time to clump up yet. 1,000 years later, in our universe, it seems like the dark matter has started to clump up a little bit, but the normal matter has not. And that's because normal matter can bump into each other and exert gas pressure, and gas pressure can fight gravity. Dark matter can't do that. So dark matter can start to clump up earlier. And so these are going to start the seeds of the galaxies and of the galaxy clusters. So you go further into the future, and the dark matter gravity is going to continue to gather up the dark matter. And once the normal matter cools off enough, it's going to be able to collapse and form galaxies using the gravity of the dark matter. And the reason why all of the yellow dots here are at the center of the dark matter halos is because the normal matter can radiate light and cool off. That allows it to collapse much denser towards the center. So we've talked about dark matter and the evidence for it and the importance of it. So now let's talk about dark energy. So when we're looking at the large-scale universe, the main two effects are going to be gravity, trying to pull everything closer together, and expansion, trying to spread everything apart. And we can see the present era of the universe. So let's take a sample slice of the universe. And we can see further into the past, and we can see how the galaxies were distributed. So what will happen in the future? Will expansion be the dominant effect, or will it change, and will gravity win? So our first model, our first idea of what might happen to the universe is called the recollapsing universe. And it's the idea that after the Big Bang, expansion was winning, but then there was enough mass and enough gravity that gravity will start to win and pull everything back into a big crunch. So here's an animation of the big crunch. So that's one idea. Let's look at another one. Our second idea is called the critical universe. What if in the future both effects would perfectly balance out? So we still have to have the Big Bang and the expansion of the universe all the way up to the present, because we have evidence for all of that. But then in the future, the two effects would be allowed to balance, and the universe would not get any smaller or larger. This universe feels nice, but unfortunately we cannot account for enough matter and enough gravity for that to happen. Even if we include dark matter, we're only at 1/4 of the gravity that we would need to halt the expansion. So now let's look at the model where expansion wins. So right now it's sounding like this is our universe. It's called the coasting universe. You have the Big Bang and the expansion of the universe all the way up to the present and into the future. The expansion just keeps going. So we look at the spacings of galaxies today. We look at spacings of the galaxies in the past and further in the past. and the data does not agree with this model. So let's have a fourth model called the accelerating universe. You still have expansion and gravity, but we're not even going to have to worry about gravity. We're going to have to add a new effect called dark energy. And dark energy speeds up the expansion faster and faster. Right. So on this graph, let's start at the present, because that's the time that we are the most confident about. And at the present, we know how the galaxies are spread out. We know the average galaxy separation. Okay. So that's this vertical axis. And if we go into the past, we can see that the galaxies used to be closer together. So we go down on the graph. And we can take that trend all the way back to the Big Bang, when all of the galaxies would have been on top of each other. So each of these colored lines represents one of those universe models. Here's the one where you have the Big Bang and it gets bigger and then gravity recollapses it, crunch. Right? The critical universe, the coasting universe where it expands forever, and our accelerating universe with dark energy. So you can see the supernova data prefers the yellow line. There are some error bars, which just represents how confident we are in our equipment and our techniques. So you could argue that a lot of those error bars overlap on the blue line. So maybe we live in a coasting universe and we don't need dark energy. But this isn't the only line of evidence that we have that says that we need dark energy. The cosmic microwave background light also implies that we have dark energy. Otherwise, we can't explain the spacing of the features. So it looks like 68% of the energy in the universe is dark energy, driving the expansion. All right. So let's go with a universe that has dark energy. What's going to happen? The expansion pushes the galaxies apart. That rate picks up and eventually they get very spread apart. There is a possibility that the expansion happens so fast that it can even rip apart galaxies or even stars. If that happens, it's called the Big Rip, but that model is not favored. So, what will happen to the universe if we live in an accelerating universe that's not going to go through a Big Rip? In about 50 billion years, most of the galaxy should run out of nebulas, so you're not going to be able to form any new stars. Low-mass stars, once they're formed, can last for about 100 billion years, so let's hop into the future and wait until all the stars are dead. You're going to end up with galaxies just basically filled with white dwarfs, neutron stars, and black holes. And I'm sure the black holes will gather up some of those other objects. Current theory suggests that even black holes cannot last forever. They will very, very, very slowly lose energy and mass. So in the very distant future, we think that even the black holes will fall apart, and that energy and that matter will just spread out even further. And your textbook ends with this lovely but depressing poem. This is the way the world ends. This is the way the world ends. This is the way the world ends, not with a bang, but a whimper.